In today's lesson, we're going to put numbers in perspective. And some of that will involve scientific notation. Scientific notation is a format in which a number is expressed as a number between 1 and 10 multiplied by a power of 10. So let's say you've got a bunch of zeros, either after or before a number. A simpler way to write it is in scientific notation. So, for example, this is, 100,000 million billion, 6,700,000,000. Right now, the decimal is here. If you count the decimal places, 1, 2, 3, 4, 5, 6, 7, 8, 9, there's 9 decimal places after the very first number. So that's what makes it 6.7 times 10 to the 9th. That's a big number, so it's got a positive exponent. If you've got a very small number, a number smaller than 1, or, smaller than 0, then you're going to have a negative exponent. So this time, our decimal is here, and we have to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 times to get it after the first non-zero number. So that's why we write negative 15. So in scientific notation, it's 2.0 times 10 to the negative 15. This number is always between 1 and 10. Okay? You wouldn't write 67 times 10 to the 8th. It has to be between 1 and 10. So you put your decimal right after the first non-zero number. Okay? Perspective through estimation, an order of magnitude estimate specifies a broad range of values, usually with one or two powers of 10, such as in the 10,000s or in the millions. So let's look at an example. It says, is the total annual ice cream spending in the United States measured in thousands of dollars, millions of dollars, or billions of dollars? Well, what do you think? Not really sure. It could be millions, it could be billions. Who knows? Let's try and figure out what this might mean. So we're going to reasonably guess that the average person has something like 50 servings of ice cream per year. Is that you? That means you have a serving of ice cream per week on average. I don't think that's me. I usually only have ice cream if I go to Cold Stone. It's my favorite. And it's an hour and a half away. So I don't go very often. But that's just me. I'm sure some people have it more than once a week. Okay. But we're saying that this is an average. So the spending we could figure out by doing a conversion. So we know that we're assuming that there's 50 servings for one person in 1 year. And I don't know, we're going to say it's $1 a serving. Now, when I go to Cold Stone, it's more like $5. But if you get it in the half gallon at the grocery store, you get a half gallon for $5 or $3. You're getting several of it. So again, we're averaging here. So we're going to say it's just $1 per serving. Make things easy. Our servings would go away, and it ends up that each person is spending $50 every year. Okay, now how many people are in the United States? We're going to say about 300 million. That is 3 times 10 to the 8th. So we get that we spend about 15 times 10 to the 8th dollars per year on ice cream. Of course, that's not the correct way to write it. If you put that in your calculator, you'd probably get 1.5 times 10 to the 9th. That's 15 billion dollars per year. And that should actually be 10 to the 10th. Okay? If you put it in your calculator, you get 1.5 times 10 to the 10th. So, ice cream spending is in the billions. That's what we've concluded. Perspective through comparisons. So, if we're talking about energy comparisons, you can read through this. For example, the energy released by a candy bar is just 1 times 10 to the 6 joules, while the energy generated annually by the sun is 1 times 10 to the 34 joules. That doesn't sound like it's a whole lot more, but it's times 10 each times greater. So it's a huge difference. Compare the U.S. population to the world population and U.S. energy consumption to world energy consumption. Okay? Well, there's a couple of things that we need to know here. So we're going to say that the world population, at least at the time I first did this problem, was about 7 billion. That's 7,000 million billion. So 7 and 9 zeros. 7 times 10 to the 9th. The U.S. population, we're going to use 300 million again. So 300,000 billion. That's 3 and 8 zeros. So 3 times 10 to the 8th. So the first thing we need to do is compare the U.S. population to the world population. So U.S. pop to world pop. 3 times 10 to the 8th. Got an extra 1 in there. Over 7 times 10 to the 9th. If you remember your exponent rules, great. If you don't, you can put this in your calculator with parentheses. If you don't, you can use a bunch of zeros. However it works for you. But if you remember your exponent rules, then this would be 3/7 times 10 to the negative 1. When you're dividing with exponents, you subtract. So 8 minus 9 is negative 1. And that is approximately 0.043. So the U.S. is about 4.3% of the world's population. That's all. Can you believe that? How much energy consumption do we use? Let's see. There's a table around here somewhere. Oh, it was back here. Okay. So, U.S. and world. So we need to compare the U.S. energy consumption to the world's energy consumption. The U.S. is 1 times 10 to the 20, and the world is 5 times 10 to the 20. Ends up just being 1/5 or 0.2. This means that the U.S. uses about 20% of the world's energy. So what are we saying here? The Americans only make up 4.3% of the world, but we use 20% of the world's energy. Kind of excessive, huh? Okay, let's look at some examples with maps here. So perspective through scaling. In this map here, 1 centimeter is equal to, on the map, is equal to 1 actual kilometer on Earth. So graphically looking at it, each little centimeter, like from here to here, would be about a kilometer. As a ratio, 1 centimeter equals 1 kilometer means a scale ratio of 1 to 100,000. Okay, kind of a long example, but interesting anyway. The distance from the Earth to the Sun is about 150 kilometers. The diameter of the Sun is about 1.4 million kilometers. And the equatorial diameter of the Earth is about 12,760 kilometers. Put these numbers in perspective by using a scale model of the solar system with a 1 to 10 billion scale. So the first thing we want to find is the scaled Earth to Sun distance. That will be the actual distance divided by our scale, which is 10 billion. So 10 to the 10th would be 10 billion. And it says the distance is 150 million kilometers. 150 million, we'll go up here and write this. In scientific notation would be 1, 2, 3, 4, 5, 6, 7, 8. So 1.5 times 10 to the 8th. So the distance from the Earth to the Sun is 1.5 times 10 to the negative 2 kilometers. Okay? We're trying to put this in perspective. We're trying to make it make sense. Can you visualize what does 1.5 times 10 to the negative 2 kilometers look like? I can't. I got no clue. Okay? So let's change kilometers to meters and see if that helps us out a bit. So we know that there's 1,000 meters in 1 kilometer, right? That gets rid of our kilometers and we're left with 15 meters. So can you visualize what 15 meters looks like? That's still pretty big. I looked it up. It's about the size of a school bus. School bus is a little bit shorter than that. So 15 meters is just slightly longer than a school bus. Okay? Next step. We need to find the scaled diameter of the sun. Okay, so the sun's diameter was 1.4 million kilometers. 1.4 million. So 1, comma there, 1,000 million. 1, 2, 3, 4, 5, 6. That's 1.4 times 10 to the 6th. So our scale diameter of the sun would be 1.4 times 10 to the 6th divided by our scale factor, which was 10 to the 10th. That's 1.4 times 10 to the negative 4 kilometers. Again, can you visualize that? I can't. Let's change kilometers to centimeters this time. There are let's change it to meters first and see if we can visualize that before we change it to centimeters. So there are 1,000 meters in a kilometer. That gives us 0.14 meters. Still a little bit hard to visualize, so let's change it to centimeters. We know that there are 100 centimeters in a meter. So multiply by 100 and we've got 14 centimeters. That I can visualize. That's about the size of the diameter of a grapefruit. Okay? So far we've got a grapefruit sitting at the front of the bus, and then a little bit beyond the back of the bus, we're going to have Earth. And so now we need to find the scaled diameter of the Earth. And it said the diameter of the Earth is 12,760 kilometers. 12,760. That would be different color. 1, 2, 3, 4. 1.276 times 10 to the 4th. So we'd take 1.276 times 10 to the 4th, divide by our scale factor of 10 to the 10th, and we get 1.276 times 10 to the negative 6. Okay? Can you see that? I can't. And that is in kilometers. So I'm going to go ahead and jump and change that to millimeters. There are 10 to the 6 millimeters in 1 kilometer. Just to speed this up a bit, okay? That gives us 1.276 millimeters. What does 1.276 millimeters look like? Let's say a large sesame seed. So with our scale factor, here's what the distance and the sun and the Earth looks like. at the front of the bus is a grapefruit. And way back, a little bit behind the bus, is a sesame seed. And that's us. Example 4 says, what is $1 billion? It's hard to visualize what $1 billion means. I mean, we know it's a lot of money, right? But what does that mean? The one way to put $1 billion in perspective is to ask a question like, how many people can you employ with $1 billion per year? Let's suppose that employees receive a fairly high average salary of $100,000. I'd be happy with that. And that cost a business, and it cost a business an additional $100,000 per year in overhead for each employee. So cost for the office space, computer, health insurance, other benefits. Okay, so the total cost for an employee a year to the company is $200,000. How many people can you employ for a year with $1 billion? Well, we just need to take $1 billion and divide by 200,000 per employee. That's $10 to the 9th billion, and I didn't say 1 times 10 to the 9th because it's just 1. Over 2 times 10 to the 5th for the employees. Gives us 5 times 10 to the 3rd employees, which is 5,000 employees. So if you had $1 billion, you could employ 5,000 people for a year. Another way to put $1 billion in perspective also points out how different numbers can be even when they sound familiar, like million, billion, and trillion. How much bigger is billion really than million? Suppose you become a sports star and earn a salary of $1 million per year. How long would it take you to earn $1 billion? Any idea? So let's take 1 billion and divide by 1 million per year. That's 10 to the 9th divided by 10 to the 6th. Gives us 10 to the 3rd, or 1,000 years. Did you realize that? If you earn $1 million a year, you will never become a billionaire. So imagine how hard it is to be a billionaire. Okay, so that's the end of today's lesson.